again. I hope this finds you and yours well. And today this is Math 2231 Alternative Delivery for the 24th of March. I am going to encourage you, as always, you might recall from the discussion we had about the economy learner that it is possible for something to be decreasing, pause play, decreasing at a slower rate. Something could be increasing and increasing at an ever increasing rate. Something could be decreasing, but then it could also be decreasing at a a rate shown here. So it's decreasing, but it's concave down, and so the rate of decrease actually is increasing. The rate of decrease is increasing, and it can be increasing, but at a slower rate as time goes on. The second derivative is what we're going to talk about in order to embrace these notions of change. So now we have a definition, and an important definition. Given the function f of x, we say the function is concave up on an interval if all of the tangents to the curve are below the graph of f of x. We say that f of x is concave down on an interval I if all the tangents to the curve are above the graph of f of x. Let's try to tie these two concepts together. So you see here the concept of thinking about the tangents. They're underneath the curve, and so that means that it's concave up. Here the tangents are underneath the curve, and so that means it's concave up. In both of these bottom examples, the tangents are above the curve. That means that it is concave down. We have another important definition today. The point x equals c is called an inflection point if the function is continuous at the point and the concavity of the graph changes at that point. Some calculus books do say that an inflection point has to have a tangent at the curve, but the notes that I'm sharing with you today do not insist upon that requirement. And the second derivative gives us insight into that. You could call this a theorem, you could call it a fact. So given a function f of x, if the second derivative of x is greater than 0 for all x in some interval I, then f of x is concave up on the interval I. Similarly, if the second derivative is negative for all x in some I, then f of x is concave down on the interval I. So, what this fact tells us is that the inflection points will be the points where the second derivative changes SIG in. We saw in the previous sections that a function may change signs if it is either 0 or does not exist. And we're talking really here about the function itself. So also then we were working with the first derivative, but changing signs where it is 0 or doesn't exist has nothing to do with the first derivative or the second derivative. It just has to do with all functions. This in turn tells us that there's a list of possible inflection points. What were those points where the second derivative is 0 or doesn't exist? And these are the only candidate points where it might change sign. Be careful, however, not to make the assumption that just because the second derivative is 0 or doesn't exist, the point will be an inflection point. We will only know that it is an inflection point once we determine the concavity on both sides of it. That is, the concavity changes. It will be an inflection point only if the concavity is different on both sides of the point. Okay, so here's the first example. For the following function, I want you to identify the intervals where the function is increasing, where it is decreasing, and the intervals where the function is concave up and concave down, and use this information to sketch the graph. That's actually quite a bit of work. The function is h of x is equal to 3x to the 5th minus 5x cubed plus 3. So pause, do some work on this problem, trying to solve it, and come back when you're ready to discuss the solution. I'm back. Let's see how you did. Here are the derivatives that you have to get, the first and second derivatives. And so what we see is that these are the derivatives, and we do want to factor them because we want to find out where these derivatives are equal to 0. Now, from the first derivative, when we set that equal to 0, there are no points where it doesn't exist. We see that there are 3 critical points for this function: x equal minus 1, x equals 0, and x equal 1. And so we're going to use the first derivative test on this, or at least the analog of the first derivative test. So here's the number line. So what we're going to do is we're going to take those 3 critical points that slices the real number line into 4 intervals: 1, 2, 3, and 4. And we'll pick a test point in each of these. We pick minus 2 in this interval, minus 1/2 here, 1/2 here, and we pick 2 in this. We plug them in to determine what happens to the SIGN. And we see that here we go from an increasing derivative to a decreasing derivative. That's going to tell us later that that is a relative max. Here we go from a decrease, let's see, here we go from a negative derivative to a, oops, now that is also another negative derivative, and so that is neither a max nor a min. And here we see that we go from a negative to a positive, and so that is telling us that that's going to be a relative min. But in terms of increasing, we have this is increasing from minus infinity to minus 1, and from 1 to infinity, and otherwise it is decreasing. And here is what I said. And we know from the first derivative test that x equals 0 is neither a relative max nor a relative min. So that is a definitive conclusion. Now, we do need to get the intervals where the function is concave up and concave down. So if you think about it, this process is almost identical to the process we use to identify for increasing decrease. The only difference is we're using the second derivative instead of the first. So the first thing we have to do is identify the possible inflection points. So we set the expression that we have for the second derivative equal to 0. And again, these points, possible inflection points, are going to be places where the second derivative is 0 or does not exist. The second derivative in this case is a polynomial, so it'll exist everywhere. And if we set it equal to 0, we find that there are, again, 3 solutions. So here are the number lines, but this time realize that we're checking the SIGN for the second derivative. And so the test points and the intervals are shown here. Here we go from concave down to concave up. Here we go from concave up to concave down. And here we go from concave down to concave up. So it looks like all of those are inflection points. And this summarizes what I said. This is the interval where we are concave up. These are the intervals where we're concave down, and all of those are inflection points. So if we put all this information together, we can draw a graph like this, and that concludes this first example. And that actually sets the stage for the second derivative test. And you might remember what I told you about second derivative tests are like power windows. They're really great when they work, but they can fail spectacularly. But let's talk about what it is. Okay, so let's begin like we did before. So suppose that x equals c is a critical point of f of x. F is a critical point of f of x such that f prime at c equals 0. I really don't like the way that's written, but this is a place where f prime of c is equal to 0, and so it is a critical point, and that f double prime is continuous in the region. You see, if f prime of c didn't exist, then you couldn't take a second derivative because there wouldn't be a first derivative. So that's another case where the second derivative test is not going to apply. But anyway, so we look the critical points of the function where it's equal to 0, and we are going to then use the second derivative test. So here are the ways we do it. If the second derivative evaluated at c is less than 0, that means concave down, then x equals c is a relative maximum. And if you think about the picture I drew last time, that comes directly from the picture as well. If the second derivative at c is positive, then x equals c is a relative minimum. And if the second derivative evaluated at c is equal to 0, then the test fails spectacularly. X equals c could be a relative maximum, a relative minimum, or neither. You really don't know. And in fact, here are some examples where you can see if this is minus x to some high even power, you see that if you take a few derivatives, you are still going to get 0, even though the max happens at x equals 0. Here is the same thing. We have y is equal to x raised to some big even power. You see the second derivative is still going to be 0 at 0, but here you clearly have a relative min. And if I looked at y equals x cubed, I'd see the second derivatives here, and this is an inflection point. And you see here the concavity does change. It changes from being negative to being positive. Okay, so we come to our next example. You want to use the second derivative test to classify the critical points for this function. And just so that you are aware, this is the same function we studied earlier, but now we're using the second derivative test to classify the critical points, so you don't have to do all your calculations from scratch. Press pause now, and we'll be back and see how you did. Let's see how you did. Well, we had 3 critical points that we were using, minus 1, 0, and 1. And in each of these, the first derivative was 0. So we can try the second derivative test. And so we plug in, and here we get it as negative. Now, if the second derivative is negative, that means that this is going to be a max because it's concave down. It looks like a max this way. It is concave down. Here it is 0. That's where the test fails. And over here, what happens? It is positive. That means it's a relative min because it is concave up. I think this just says what I said. The second derivative at x equals 1 is negative, so that is a relative max. This is positive. The second derivative at x equals 1 is positive, so it's a relative min. And this is where it fails. So whenever it fails, you have to resort to the first derivative test. Now we already did that, and we saw that this critical point is not a relative extreme at all. It is neither a relative max nor a relative min. Okay, let's do one final example for this lecture. So here we have a function. For the following function, find inflection points and use the second derivative test, if possible, to classify the critical points. If it's not possible, you have to use the first derivative test. Also determine the intervals of increase and decrease for this function, and the intervals of concave up and concave down, and sketch the graph of this function. Actually, quite a bit to do here. The function is f of t is equal to t times the quantity 6 minus t whole to the 2/3. This one will be interesting for a couple of reasons. So please press pause now. Let's see how you did. if we take the derivatives and simplify, we get f prime of t is equal to this expression. And here we get f double prime of t simplified is equal to this expression. Again, since you're setting these things equal to 0, algebra is your friend, so you do want to do these simplifications. Now, the critical points happen when the first derivative doesn't exist, and there is a point where the first derivative doesn't exist, that is t equals 6. And it also, a critical point happens when the numerator is equal to 0, and that is at t equal 3.6. Now we can't use the second derivative test on t equals 6 because the first derivative didn't exist. And so we'll have to use the first derivative concepts and first derivative test to get the information in a sketch graph. But if we look at f double primed evaluated at 3.6, we get that this is negative, and that tells us, according to the second derivative test, that t equal 3.6 is a relative maximum. Okay, so now what we're going to do is we're going to use those critical numbers, and we're going to look at this. And there were two critical numbers, so that divides the real number line into 3 subintervals. Here's the first one, there's the second one, here is the third one. And what we're going to do is we're going to see for test points what happens. So here what happens is the first derivative is positive, and then it is negative, so that means that indeed we do get a relative max. And over here we go from negative to positive, and that tells us that this, so it's going from negative to positive. And again, it doesn't matter that it doesn't exist there because the critical point was one where it did not exist. But you see that that is also a minimum because we went from negative to positive with the first derivative. Okay, now let's finish the problem. The possible inflection points are where the second derivative was equal to 0 or where the second derivative did not exist. That means that 6 was a possible inflection point. And so what we have here is 2 possible inflection points, and so that will divide the real number line into 3 intervals. There's the 6 and there's the 7. The 6 is over here and the 7.2 is over here. And now what we're going to do is we're going to evaluate what is happening with the second derivative. Now here at 6 we see that the concavity is concave down and concave down, so it doesn't change at 6, but it changed from concave down to concave up at 7.2. So the concavity does change only at t equals 7.2, so that is the only inflection point for this function. And I will be asking you to find inflection points. And so here's the graph, and you see that we have really a cusp at the point 6, 0. And we should note that the change in concavity at t equals 7.2 is hard to see, but it's just subtle. So now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. Take care.